So good morning, everyone. So I'm Serge Vaudonnet. I'm pleased to welcome you to this session on messaging and message ranking. We'll have 3 talks today, and the first one is entitled Unique Path Identity-Based Encryption with Applications to Strongly Secure Messaging by Paul Rosser, Daniel Slamanik, Christoph Striex, and Paul is giving the talk.
Yeah, thank you very much for the introduction, Serge. We talk about messaging and the building blocks that are used in messaging, and we directly dive into the setting, in which we have Alice and Bob communicate via an insecure channel, and for this, Bob generates a key pair, sends over the public key to Alice, and Alice uses that public key to encrypt her messages, sends the resulting ciphertext back to Bob, and then after sending the ciphertext and receiving the ciphertext respectively, both users will update the components of the key pair on their side. And it is important to note that for this update, they will both use the ciphertext that they either send or received, so these ciphertexts influence the outcome of that key update. The purpose of updating the keys is that whenever the adversary corrupts the secret key of Bob, the adversary should not learn anything on the previous versions of that secret key, and in particular not on the payload that is encrypted with the corresponding public keys. So this idea or this goal is usually referred to as forward secrecy. But we want to have a second property with these key updates, and for this we consider that Alice encrypts another payload with the updated public key, sends the ciphertext to Bob, but in this case the adversary drops the ciphertext and replaces it with a forged ciphertext, sends it to Bob, and again Alice and Bob will update the components of the key pair. As I mentioned before, we want that the corruption of a secret key on Bob's side does not reveal any information on the previous secret keys or on payload that was encrypted to the corresponding public keys. But now we also want, since the ciphertext influenced the key update, that the 2 components of the key pair are diverging after the key update. And that means that the public key is basically independent of the secret key, such that future payloads that will be encrypted with the public key will also not be leaked to the adversary, even if the secret key on Bob's side is revealed. Okay, so this primitive is called Key Updatable Key Encapsulation Mechanisms, or short Key Updatable KEMs, and it was proposed and used in previous work on secure messaging. There has even been a work that showed that this primitive key updatable KEM is both sufficient and necessary to certain notions of strongly secure messaging. And we will look at how to build this building block. I finally want to mention that key updatable KEMs are stronger than what we call updatable public key encryption, or UPKE, because this UPKE primitive doesn't provide this strong diverging property, such that secret key and public key are independent of each other if the update was conducted with different input ciphertexts. Okay, so how do we build key updatable KEMs? We build it from something that we call Unique Path IBE. I will let you know what it is by explaining how the workflow or how the communication between Alice and Bob flows. So for this, Bob generates a key pair, public key and secret key, and Bob can use the secret key to delegate subordinate secret keys. We see here 7 different paths, how such a delegation could look like, and the algorithm that Bob uses for this takes the master secret key and delegates a secret key with an identity string ID1. And that secret key that is delegated now only works for that identity string, and we will learn what works means in a second. Although we just have, or I just show you 7 delegation paths on that tree that you see here, I want to mention that the identity string comes from an exponentially large identity space. Just for presentation, I just summarize that as 7 paths here. Okay, so after Bob generated the key pair, he could also send the public key over to Alice, and Alice can use that public key also to delegate subordinate public keys using basically the same algorithm, but this time taking the public key, the master public key, and an identity string, and delegate a public key that only works for that particular identity string ID1. Alice can continue doing that with a second identity string to delegate from this intermediate public key pk ID1 a second public key pk ID1 concatenated ID2. And this again looks like that. We have a cascade of trees, or basically a big tree, and that's the resulting public key that we consider for now. On Bob's side, he could do the same thing, delegating with the same identity string, or alternatively use a different identity string. And in this case, when Bob uses the intermediate secret key skID1 and delegates it with an identity string ID prime, he will obtain a secret key ID1 concatenated with ID prime. And in that case, when the two identity strings differ, the result is that whenever Alice encapsulates with the lowest public key to these two identity strings, then the secret key on Bob's side with the different identity string will not work for decapsulating the ciphertext. And in particular, if that secret key is ever corrupted, then this doesn't reveal information on the keys that are encapsulated in these encapsulations to the public key with a different identity string. Okay, so we call this primitive unique path identity-based encapsulation. And those of you who know what HIBE or hierarchical identity-based encryption is, unique path IBE is basically the same. The only difference, and that difference will turn out to be very crucial, is that we only permit one delegation per secret key. So you see here that there is just one path of delegation from one secret key to another, and that path can be continued infinitely. And that makes it that's the reason why we call it unique secret key or unique path IBE. I just want to mention again that the delegation here is always based on an identity string from an exponentially large identity space. So our contributions are that so far HIBE, so hierarchical identity-based encryption, was used to build what we call UPIBE, unique path IBE. And we propose two constructions. The first one showing that actually IBE suffices, so with a hierarchy depth of 1, suffices to build bounded depth UPIBE. So that means we only need, as a building block IBE, to build a unique path IBE with a bounded depth of delegation, where the bound can be any polynomial. And it suffices to use bounded depth HIBE to build unbounded depth unique path IBE. Okay, so that's the contributions. How do we build UPIBE? And for this, we first consider the bounded depth case with a parameter Q that sets the bound how many sequential delegations we permit. And in order to explain this, I start with the key generation that generates a UPIBE public key and a secret key. And these UPIBE public keys and secret keys consist of IBE key pairs. And we generate for this one IBE key pair per UPIBE delegation depth. And the UPIBE public key now consists of in that case, when Q is 4 IBE public keys, and the secret key consists of 4 IBE secret keys. The next step is to understand how delegation works. So UPIBE delegation works as follows. We have a UPIBE secret key on the upper part here, and we delegate a UPIBE secret key with the identity string 1. And for this, we slightly change the structure of that UPIBE secret key. First of all, we remove the IBE master secret key on the first level. But we take it and delegate from it via IBE delegation one IBE secret key that is delegated to the UPIBE identity string, delegation identity string ID1, but with a suffix bit 0, and we delegate a second IBE secret key with the UPIBE secret key and the suffix bit 1. And we basically use these two delegated secret keys to replace the IBE master secret key in the first component of the UPIBE secret key. Okay, we can continue doing that, taking that UPIBE secret key, delegating it again with an identity string ID2, and we repeat the basic or the same approach by first removing the first delegated IBE secret key in the first level and the master IBE secret key in the second level. We again take that master IBE secret key, delegate to subordinate IBE secret keys, both with the UPIBE identity substring that we use for delegation, but one with the suffix bit 1 and the other one with the suffix bit 0, and these two delegated secret keys replace the IBE master secret key in the second level. We would continue to do the same thing for the third level, just taking the identity string ID3, again removing the first component of the previous level and the full master secret key, master IBE secret key on the third level, and replacing that current level's master secret key with the two delegated IBE secret keys. You will understand why we do this in a couple of seconds, just for now accept that it works. The next step is to understand how encapsulation works. For this, we take a look at the UPIBE public key that consists of the 4 components of the IBE, or these 4 IBE master public keys. And we want to encapsulate to an identity string that consists of the 3 sub-identity strings, ID1, ID2, ID3. And for this, we take the 4 IBE master public keys from the UPIBE public key, and we delegate from each of them one subordinate IBE public key. The first one that we take is the one from the first IBE master public key, delegated to the identity string ID1 with suffix bit 1. The second one is delegated to basically the same one, just with the identity string ID2. But the third one now is delegated to the identity string 3 with the suffix bit 0. Okay, this is important to remember. The fourth IBE master public key will not be used for an identity string of length 3. And now, in order to compose the ciphertext, we first secret share the payload. And since we talk about key encapsulation here, we just basically secret share a symmetric key. And the symmetric key is just 3 random components and then XORed, and that's basically the secret sharing that we have here. But yeah, that's the basic principle. And now we take the 3 delegated IBE public keys and encrypt each of these secret shares with one of the public keys. Okay, that's encapsulation. How does decapsulation work? For this, we take a look at the public key and the corresponding secret key, and we see, when we gray out the IBE secret keys that we don't need for that we have one component for each, or one secret key component for each public key component with which we encrypt it, so we can basically decrypt all 3 components, undo the secret sharing, and we obtain back the payload. Okay, that's super simple. Now the question is, why does our construction look the way it does? So the first question that we ask, or that I want to explain, is why do we have one IBE instance per depth of the UPIBE delegation? That may sound a little bit too much. And for this, we look at the delegation tree of our UPIBE key hierarchy. And we take a look at the delegation of our identities, or of our UPIBE secret key with identity string ID1, ID2, ID3. So these are the identities here. And we take a look at a second UPIBE secret key. And that second UPIBE secret key is the one that is corrupted. And we want that all the ciphertext encrypted to the first green secret key here, the green UPIBE secret key, should stay secure even if the orange secret key here is corrupted. The problem is that the first and the third level of IBE secret keys are entirely captured in that corrupted secret key here. And so we could compile these components of the corrupted secret keys. You can just take a look. They basically look the same in the first and third and also in the fourth level of the IBE underlying components. But the second level is different here, and we have to make sure that whenever there is just one bit of difference, there needs to be a difference in the underlying delegation, and that's the reason why we have one component per level, or sometimes even 2 components, and that's the second question that I want to answer. But first of all, the first question is we need at least one component per level. The reason is we don't want to allow an adversary to compile secret keys for challenges from corrupted UPIBE secret keys. So the second question is, why do we have two delegations on the IBE layer per IBE instance? So we see here again our green UPIBE secret key that has two secret key two IBE secret keys in the third level. Why is this the case? And for this, we consider an extension of the green delegated UPIBE secret key, and that extension is just one further UPIBE delegation to the fourth level with an identity string ID prime. And what we want to have is that, that all ciphertexts encrypted to the green UPIBE secret key should stay secure even if an extended or further delegated UPIBE secret key is corrupted. That's also what HIBE would require us to do. And for this, we have to, or we can see that although the first two levels of IBE secret keys are again entirely captured or contained in the orange UPIBE secret key, but for the third level, we just have the IBE secret key component in the orange UPIBE secret key that helps us to decrypt the single components of all except for the last ciphertext component of our UPIBE secret key. That might be a little bit complicated. For the details, probably look at the paper. But the basic idea is that the first component that always is the one that is used for the last level of a challenge or of any ciphertext, that one is not contained in the extended delegated UPIBE secret key anymore. And that basically makes sure that a UPIBE secret key cannot be used to decrypt any prefix UPIBE secret keys or previous versions of that secret key. Okay, that's the idea. Some ideas how we extend that construction to the unbounded depth case. So we remind ourselves that the UPIBE public key and secret key consists of a list of IBE public keys and secret keys, and we can't extend that list infinitely, or at least unbounded with an unbounded polynomial. And so what we have to do is we have to extend that list of IBE key pairs to an unbounded list. And the idea is that we use something that is, that is somewhat related to the idea of how FS, or forward secure public key encryption, works. We basically take an HIBE key pair, public key and a secret key, and we delegate from that, first of all, with a dynamic delegation mechanism, the public keys and secret keys that we then use in the same manner as we did it for the bounded case. So we again delegate two IBE public keys and secret keys when we want to create, or when we want to delegate and we want to create ciphertexts. And for this, it suffices to have a single bounded depth HIBE public key in the UPIBE public key and a single bounded depth corresponding HIBE secret key in the UPIBE secret key. We extend that even with multiple delegations in epochs. It's not important to understand that right now, but essentially our UPIBE delegation path, which is the orange one here, is embedded in this bounded depth HIBE structure such that we obtain an unbounded number of delegations. That's basically the idea. So a quick summary and an outlook. Our bounded depth UPIBE construction can be built from two bounded collusion IBE, and there are very efficient constructions from DDH such that we can even aggregate secret keys and ciphertext to make them constant size. Our public key is still a little bit too large for practical applications. For the unbounded case, we can build it from kappa bounded depth HIBE, where kappa is linear in the security parameter. And you may think that could be problematic if we want to build that from selective security to adaptive security. But with a somewhat nice trick, we can use the random oracle to use bounded depth HIBE with selective security to build unbounded depth UPIBE with adaptive security. One final comment. If you are an expert in bounded depth HIBE constructions, please talk to me, because we have a couple of ideas how to exploit the structure of underlying HIBE constructions to aggregate public keys and ciphertexts and secret keys. But so far we didn't dig deep enough into these HIBE constructions because we basically use all of these things in a black box manner. Thank you very much for your attention.
Is there any question? No question? Okay, so let's thank the speaker again. So we move on to the second talk of this session, which is entitled End-to-End Secure Messaging with Traceability Only for Illegal Content. It is by James Bartusek, Sanjam Garg, Abhishek Jain, and Guru Vamsi Polishala. And Guru Vamsi is here. So you can present the sponsors.
I'm not sure how to get this to work. I can talk about this slide. I just heard about it, but.
Is this yours?
Yeah.
Yes, it's here.
I don't know. I can start reading names. Apple, Huawei.
Still, okay.
Okay,
Thank you.
so finally. So today I want to talk about end-to-end encrypted messaging with traceability only for illegal content. So I want to start the talk by briefly mentioning this debate over encryption that's been happening for quite some time. On one side, you have privacy advocates and other tech companies which have been strongly pushing for end-to-end encryption and end-to-end encrypted cloud storage services. On the other side of this debate, you have law enforcement, which argues that the deployment of end-to-end encryption is going to interfere with their prosecution of criminals. So a disclaimer is that this is a much more nuanced debate than I have the time or expertise to talk about. If you want to learn more about this, there are some very good RWC talks this year and last year. But I'll try to briefly summarize what the two sides of the argument are saying. So the privacy advocates say that, look, there's just no good way to implement backdoors in these systems. All proposed systems so far are susceptible to abuse, and surveillance and censorship is a real threat. And assurances by tech companies that this is not going to happen is simply not sufficient. So on the slide, I have a screenshot of a New York Times article which talks about how Apple started building data centers in China. But what happened was state employees eventually became administrators in these data centers. And this allowed the government to essentially gain unrestricted access to the locations, the files, like emails, photos, and contacts of millions of Chinese residents. So this is the kind of thing that can happen if we don't deploy these things correctly, and this is explicitly something we should really try to avoid. So the flip side of the argument, which is made by law enforcement, is that, look, you can't ignore the negative impacts when you deploy end-to-end encryption. On the slide, I have a screenshot of an international statement that was signed by high-ranking officials from the US, the UK, Japan, Australia, and India. And essentially what they said was, look, we have a lot of reports on CSAM that come in every year, and close to 2/3 of the CSAM reports, CSAM is child sexual abuse material, which is illegal content, and say that, look, close to 2/3 of these come from Facebook, and if you're going to deploy end-to-end encryption, this is going to interfere with our ability to prosecute these, and we're essentially going to lose access to these reports. So essentially they said, look, if you're going to do this, you need to do it in such a way that we're still going to be able to prosecute criminals. And if we ask for the data of some individual who is, let's say, under investigation, you need to be able to give us that. Okay, so can we as cryptographers, right, find a middle ground that's going to make both sides of this debate happy? In particular, at a very high level, right, what we want to do is identify bad actors in the system without compromising the privacy of honest users. Again, another disclaimer, we don't think any proposal that exists is safe for deployment yet. There are still a lot of problems with them, and hopefully this work is one step towards something that could maybe eventually be deployed. Okay, so how does content moderation work today? Let's say you didn't have end-to-end encryption, right? The server can essentially see all the messages that are being exchanged. What's going to happen is the server is going to be given a database of illegal images. So these are not going to be illegal images in the clear. They're actually going to be these things called perceptual hashes. These hashes are not cryptographic by any means, and the reason you need it is because you need these hashes to be resistant to small changes in things like cropping and rotation, so not cryptographic in any sense. So much so that you can make a dog and a picture of a girl hash to the same thing, and this person on Twitter actually put the hash of the image itself in the image. Okay, so now I said, there's no inter-encryption, so the server is going to be able to view all messages being exchanged. So let's say you have Alice, who has a message. She's going to send it to Bob. What she's going to do is she's going to establish some sort of encrypted channel with Facebook, and Bob is going to do the same with Facebook. And now Alice is going to send this message. Facebook is going to look at this message, compute the perceptual hash, check if there's a match in this database of illegal images that it was given. And if there is, it's going to bring in a human reviewer. This is to check for false positives. So the human reviewer is going to say, okay, is it actually illegal content? And if it is, then this image, along with Alice, is going to be reported to law enforcement. So what happens if you have end-to-end encryption, right? Now the server can no longer see this image, so how is it going to compute this perceptual hash? So essentially all existing techniques that we have for content moderation seem to be incompatible when you introduce end-to-end encryption. One thing I want to mention is there's an inherent limitation to the approach even without end-to-end encryption, where the server can actually see all of these images in the clear. And what a malicious user can do is always use steganography in their communication to hide what they're communicating. So let's say Alice and Bob are malicious and they're colluding and they agreed on some steganographic technique. What they can do is embed a malicious image or a harmful image inside a harmless or a seemingly harmless image, and the server is not going to be able to detect this. And this issue is going to persist even if you use the fanciest of cryptography. So a question we should ask is, who is moderation really targeting? Because typically in cryptography, you assume that the adversary is like, the smartest and is going to use the optimal technique. Turns out there are still 18 million plus reports every year of illegal content on these services. So law enforcement says, look, we still want access to these reports. Deploying end-to-end encryption is going to hinder that. And so you need to find a way to make both sides work. Okay, so if we wanted to do end-to-end encryption alongside content moderation, what do we really want? So we can start by listing out some bare minimum requirements. This is not going to be a complete list, but we want at least this much. So what we want is the server learns no information about the messages being exchanged, and the originator of a forwarded message should remain anonymous. What do I mean by the second property? So let's say you have 4 parties, Alice, Bob, Charlie, and Eve. Alice has a message, she forwards it along the chain all the way to Eve. Suppose Charlie and Eve collude, they shouldn't learn any information about who sent the message M. In particular, in their eyes, it could have been Alice or it could have been anyone else in the system. And of course, if the server colludes, they have some more auxiliary information because the server has a graph of messages being exchanged. This might reduce the anonymity set, but you still want the advantage of guessing who sent the message to be no better than just guessing randomly. So standard end-to-end encryption messaging already satisfies these 4 properties. If this is all we wanted, we don't need to do anything, but we haven't done anything for content moderation. So let's try to add something. So the property that roughly what we would like is if a user receives some content, even if it was forwarded along a very long chain, and this final user reports it, we want the server to be able to identify the originator of this message without any help from users along this chain. So essentially, we want to go all the way back to the first person who sent this message, if a report was sent to the server. So if you're only interested in feasibility, you can do this with group signatures. I'll describe how you do this because it'll also set the stage for what I want to do next. But there's been a long line of work on traceback for end-to-end encryption, which achieves this along with some very, very nice properties. So this started with message franking sometime in 2017, and message franking aimed to solve the problem, which was that, look, if you have end-to-end encryption, you, in some sense, automatically get deniability, and you want to be able to say, look, when you make a report, you want to prove to the server that you actually received this message and you're not just, like, let's say, simulating the transcript. And very cool work. It was able to achieve this using some very efficient techniques. And then this was followed up by a line of work on traceback, which actually achieves all these three properties, which is you can go all the way back to the original sender of a long forwarded chain of messages with just one report from the final end user. OK, so let me talk about this group signature construction, which can achieve these properties. So what is a group signature? Essentially, a member of a group can anonymously sign on behalf of the entire group. But at the same time, there's a group manager who can identify the sender of a message. So the signer is anonymous to everyone except the group manager. So let's say you have a bunch of parties. They go to the group manager. They first register as a group. They're going to get some keys. And so Alice is going to use her key to sign her messages. She's going to output some sigma. And importantly, you only need the master public key to verify the signature, which is kind of independent of the secret keys or the public keys of each of these users. But then there's a group manager who has a master secret key. And given the signature, the group manager can identify the signer of any signature. And so given this master secret key and a signature, the group manager is going to output the public key of Alice, let's say, who was the one who signed this message. OK, so if you have group signatures, how would you do content moderation? It's very simple. So what you would say is, OK, look, all the users in my messaging service are going to come register with my group manager as members of this group. When they send messages under this end-to-end encryption, whatever your favorite protocol is, they're going to attach a group signature alongside this message. And so when a report occurs, the recipient is going to send the message along with the group signature to the service provider, who's going to be able to run this tracing algorithm because they have the master secret key. And if it is actually harmful content, they can take punitive action against the sender, so in this case, Alice. So we've achieved the three properties that we had written out, which was if there's no report, we want a malicious server to not learn any information about the messages being exchanged. And this is guaranteed because everything sort of stays inside the end-to-end encryption. And again, if there's no report, we want the originator of forwarded messages to remain anonymous. This is guaranteed because in group signatures, you can't identify the signer. So even given sigma, you're not going to be able to figure out who sent this message. And finally, if a user receives some content and reports it, the server should be able to identify the originator. This is because the server has the master secret key. OK, but we should stare at this definition, because this is essentially what all prior work achieved, and ask, is this definition really sufficient? Can this, if you deployed a system which satisfies these definitions, is it actually resistant to coercion or surveillance or abuse? An important point in this statement is that if a user receives some content, it could be harmless content or harmful content. There's no sort of restriction on what kind of content was received. So what happens when a malicious server and a user try to collude, right? So imagine you're in some authoritarian regime, you're trying to organize a protest, let's say. If your message for organizing this protest got forwarded, let's say, to someone colluding with law authorities, they can essentially de-anonymize you and identify who the sender of this message was. And again, this is something we explicitly want to prevent. So let's try to strengthen this definition. What we want to say is if a user receives some illegal content, even if forwarded and reports it, only then can the server identify the originator. How do I define illegal? This is, again, a topic which I would argue is still an open question. But what we're going to do in this work is define illegal content in the same way that we did in the non-end-to-end encrypted case, which is there's a database of illegal content which the server is given, presumably by some third party. And if this message that was sent was in this database, we want to identify the originator. If it's not, then we don't want to identify the originator. So the fourth point is going to say the originator of harmless content, which is if the message was not in this database, they should remain anonymous, even if the receiver and the server collude. OK, so how do we achieve security against malicious servers now? This is going to be the rest of the talk. So let's go back to this approach of group signatures and how we built content moderation from it. What was really going wrong here, right? The problem was that the server had this master secret key, which allowed it to decrypt or de-anonymize the sender of any message, not just illegal messages. So what we're going to do is try to tie its hands. And the high-level design philosophy is, again, we want to explicitly avoid any sort of master secret key in the system, because there's just not going to be any server accountability. In particular, we actually want to say that these keys by the server can be generated in a malicious manner. And the server should only be able to de-anonymize the senders of bad messages. So there was this very interesting work on pre-constraining encryption at ITCS last year. And essentially what they said was, look, in standard public key encryption, you can decrypt any message that was encrypted to your public key. But what pre-constraining encryption says is you can only decrypt the message if the message satisfies some sort of predicate. So it could be that, oh, if the first 10 bits of the message were 0, only then can you decrypt the message. So we built on this framework and introduced something called pre-constrained group signatures. I'm going to define what they are in the next slide. They look exactly the same as before. So you have a group manager, but the only change is that in the key generation phase, the group manager needs to supply a database of illegal images for which signers can be identified. So the master public key and the master secret key are essentially going to depend on this database. And we also want that the public key should not leak this database D, because these are actually illegal images and should not just be distributed to the public. And we can also enforce that this database D that the server uses is signed by some third-party authority, let's say the National Center for Missing and Exploited Children in America. So what's going to happen is exactly as before. Oh, by the way, this key generation can be fully malicious. So users are going to update their keys. Alice is going to use her key to sign. But the crucial difference is that when the group manager tries to run this tracing algorithm, it's only going to be able to identify the sender if and only if the message was in this database that the group manager chose in the beginning. And this is essentially this pre-constraining notion that we've introduced to group signatures. So if you had pre-constrained group signatures, how would you do content moderation? Exactly the same as before. Inside the end-to-end encryption, you're going to attach these group signatures. And now when a report occurs, you have this guarantee that the server's trace algorithm is only going to work if the message that you signed was actually in this database of illegal content. And so the privacy of honest users, by honest users I mean people who don't sign illegal messages, is unaffected. OK, so how do we pre-constrain group signatures? I'm going to describe a compiler where, for pre-constrained group signatures, where I'm going to start off with a generic construction of group signatures and modify it to essentially pre-constrain it. So in this generic construction, you have this master public key, which contains two things. The first thing is the verification key of a signature scheme. This could be your favorite signature scheme. And the public key of some public key encryption scheme. Again, your favorite public key encryption scheme. So the ciphertext, so the group signature has two parts. The first part is a ciphertext, which is an encryption of the client's public key, which is going to be the client's identity, under the server's public key. And after this, you're going to attach a proof, which essentially says the following, which is, I know a server signature, sigma, on my public key. I encrypted my public key using some randomness R to the server's public key. And I know the secret key corresponding to the public key that I just encrypted. And the message is going to show up as a tag in the NUZIC. So what do these three things serve? The first one says that only group members can sign, because when you register with the group, you get a signature on your public key. And the second thing says that the group manager can always trace, because they have the secret key to which you encrypted, the PKS. And the third thing says, it's again unforgeability. You shouldn't be able to use somebody else's identity and encrypt it there. OK. So what is the issue here, right? So in this, if you stare at this construction, right, the issue is that in this ciphertext, right, which hides your identity until unless there's a report and the server can decrypt, it was just standard public key encryption, so the server can always decrypt. So this is really where we want to try to pre-constrain the scheme and introduce some sort of, or tie the hands of the server here. And the way I'm going to do it is by replacing two things. So I'm going to replace the public key in the master public key with the first message of a PSI scheme. I haven't described what this PSI scheme is. I'll just get to it in a second. And the ciphertext is going to be the second message of a PSI scheme. So what does this PSI scheme look like? It's very simple. So you have a server with a database D, you have a user with a message M, and we want this variant of like circuit PSI where the server learns a label, which is like PKC, if the message M is in this database D, which the server had. And we want some other nice properties from this PSI, which is that it's 2 rounds. The first round is reusable because we really want to be able to create these ciphertexts in a reusable manner. And it's also desirable to have these ciphertexts to be constant size and the time for the second round message to be constant size because we're going to be creating proofs about these things. So if you stare at what this PSI construction is doing, essentially it's only going to allow the server to learn the public key, which is PKC, if the message was in the database D. If not, it's going to learn nothing. Okay, the question is, do we have such a PSI scheme which satisfies all these properties? And the Apple PSI scheme, which came out a couple of years ago, satisfies most of these properties. We have to work a little bit harder to get to where we want. But a caveat is that the size of the master public key is proportional to the size of the database. This can get quite large, but you can think of these as system updates. So whenever you update your app or your software, it's going to come along with that. And so what happens to the proof here, right? So it's going to be modified, just the second point, which is you just show that the CT, which is the second round PSI message, was computed correctly. Everything else remains the same. So final touches if you want to actually instantiate this scheme. So you're going to pick the right signature scheme and the right proof system to kind of play well and be concretely efficient. So we use structure-preserving signatures along with the Grazia high proof system. How do we perform when we use these things? Signing takes about 10 milliseconds. Verification takes about 40 milliseconds. This might be a little bit far away from what you want for messaging, but I would argue that's reasonably close. Okay, so takeaways, right? So this is something I want to spend a little bit of time on. So the constructions, when you want to build these things, are very exciting. You can come up with like notions of like forward security and all these nice cryptographic notions and guarantees that you want. But I would argue that at least here, right? Because this is the kind of research that's going to have a real impact and like going to touch the lives of real people very, very directly. And so we should be really careful before deploying these systems. And we should really question the definition and argue whether this is the right thing. Is this actually going to give us the right privacy guarantees that we would want? I believe the right way to go about this is to talk to both sides of the debate and get some formal requirements from both parties and then try to build this instead of just saying, okay, we're just going to come up with a definition and, okay, this is just going to be secure. Because being secured according to the wrong definition is simply meaningless. Thank you.
Is there any question?
Is it on? A quick question about updatability. So it seems that now you have to fix statically the database once and for all. Is there something non-trivial that can be done if I come to you with a new database, or do you have to regenerate everything?
So currently we have to regenerate the database, but it is an interesting question. I think at least from a PSI perspective, where you could say, oh, I have this updatable PSI notion without communicating the entire database. We thought about it for a little bit, but we didn't make much progress.
All right, thanks.
I have a question in a similar direction, also about the database. How do you ensure that there's only child sexual abuse material in there? After all, we're talking about state actors,
right.
So there might also be state actors sneaking politically undesirable content.
Right. I agree, and this is indeed an issue that needs to be fixed. So currently what we say is, look, there is a separation between the person preparing these keys and the person preparing the database. So in some sense, you need a way to define what illegal content is. The way we did it was there's this independent party, the National Center for Missing and Exploited Children, for example, who is the one saying, look, this is illegal content which you should look out for and monitor. What we say is you need a signature from that party on your database if you want to actually generate keys and if you want to use it. So clients can publicly verify that everything that can be traced was signed off by this organization. But if this organization itself is corrupt, there's really nothing we can do. And it is an important question and something we should look into to sort of reduce the trust assumptions here.
Okay, last question.
I had a follow-up. I didn't get our clients verifying the signature from this CMAC or
so when you get the master public key, you can just verify it. You can say the master public key comes with kind of a proof which gives it, and you should be able to verify it. Yeah.
Thank you.
Okay, so let's thank the speaker again. So now we move on to the final talk of this session. It's entitled Asymmetric Group Message Franking, Definitions and Constructions by Jungzhu Lai, Gongxian Chen, Zhenggan Huang, Xiuming Yu, Xi Mu, Jiang Wang, and the talk will be given by Xuan Han, who is not a co-author, but who represents the authors. Please.
Thanks for the introduction. Good morning. I'm the proxy speaker, Xuan Han. I will make the presentation on behalf of the authors who regret not being able to attend the conference by person. The title is Asymmetric Group Message Franking, Definitions and Constructions. And the authors are Junzuo Lai, Gongxian Zheng, Zheng'an Huang, Xiuming Yu, Xin Mu, and Jian Wang from Jinan University, Pengcheng Lab, and the University of Hong Kong. So firstly, I will introduce the background and the motivation behind this research. In recent years, secure messaging applications have gained huge popularities for both individual and group conversations. Billions of people communicate with each other daily via messaging applications such as Facebook, Messenger, and Twitter. Confidentiality and integrity have been extensively studied in these applications. However, these messaging applications are often misused for spreading malicious information, such as online bullying, spamming, phishing links, and misinformation. Facebook Messenger introduced the concept of message franking, which provides the functionality to report abusive behavior. This allows for appropriate punishment of senders who misuse messaging applications. Here, we will review the security properties of messaging franking introduced by Tyagi et al. And there are two key security notions to consider. The first is accountability, which enables the receiver to report any malicious messages to a moderator, such as a platform or a trusted third party, and ensures that no fake reports can be created to frame an honest sender. To formalize accountability, two specific properties are used: sender binding and receiver binding. Sender binding guarantees that any sender should not be able to trick receivers into accepting unreportable messages. And the receiver binding guarantees that any receiver cannot deceive the judge to frame the innocent sender. The second property of messaging franking is deniability. Essentially, deniability ensures that when a malicious message is reported by the receiver, only the moderator can verify the validity of the report. This means after a compromise, the sender can technically deny sending the message, potentially avoiding negative consequences of embarrassment. And deniability is formalized with three special properties. The first one is the universal deniability, which guarantees deniability when no secret keys are compromised. And the receiver compromised deniability ensures deniability when the receiver's secret key is compromised, and the judge compromised deniability considers deniability when the judge's secret key is compromised. And there are mainly two kinds of message franking: symmetric message franking, SMF, and asymmetric message franking, AMF. The key distinction between them is that AMF offers third-party moderation, allowing the separation of the platform and the moderator. However, current AMF solutions only considered one-to-one communication. There has been no research on applying message franking to group communications. Now, we turn to the contributions. In this paper, we systematically explore message franking in group communication scenarios, and the contributions are listed as follows. First of all, we introduced a new primitive called asymmetric group message franking, or AGMF for short. and formalize its security notions. Secondly, we present a variant of key encapsulation mechanism called hash-proof system-based CAM supporting Sigma protocols, or HPS CAM Sigma for short, and provide a construction based on the DDH assumption. The construction can also be extended to be built based on the key-linear assumptions. And finally, we provide a framework of constructing AGMF from HPS CAM Sigma as a building block and show that it achieves the required security properties. When the size of the receiver set is 1, we also obtain a framework of constructing AMF from HPS CAM Sigma. Here we make a comparison on AMF and our AGMF. The main differences are that, firstly, in AMF, the adversary can corrupt only one receiver, while in our AGMF, the adversary can adaptively corrupt multiple receivers. And secondly, AMF does not take receiver anonymity into consideration. We consider it in AGMF so that the receiver can report malicious messages to the moderator with less concern. And thirdly, our constructions can be based on standard assumptions like DDH or K-linear. Then let me introduce the primitive of AGMF. An AGMF scheme contains 9 algorithms. Setup is an algorithm for generating public parameters, and KGJ and KGU are the algorithm for generating key pairs for the judge and the common users, respectively. Frank, verify, and judge are 3 algorithms for the signature generation, the receiver's verification, and the judge's verification, respectively. Forge, rforge, and jforge are the other 3 algorithms to forge signatures. In a nutshell, the sender will invoke the algorithm Frank to generate signatures for receiver set S. And any receiver can call verify with its secret key as input to verify the signatures. If some receiver outputs some malicious messages to the moderator verifies the report with algorithm judge. And the algorithm forge, rforge, and jforge are not intended to be run by these users or judge. Their existence guarantees deniability in particular compromise scenarios. We consider 3 kinds of security requirements for AGMF: accountability, deniability, and receiver anonymity. Since some of them are similar to those of AMF, here we only show the differences. Firstly, AGMF considers corruption of multiple receivers. Specifically, its receiver binding requires that any corrupted receivers, not just a single receiver, cannot deceive the judge or the other honest receivers to frame the innocent sender. And its receiver compromise deniability requires that any corrupted users in the receiver set, not just a single receiver, are able to create a signature such that for other parties with access to these corrupted user secret keys, it is indistinguishable from honestly generated signatures. And secondly, AGMF considers receiver's anonymity. It requires that anyone, except for the receivers in the receiver set, including the judge, cannot tell which receiver set a signature is generated for. And thirdly, AGMF supports adaptive security. In all our security models, the adversary is allowed to corrupt the receivers adaptively. Finally, I will show how to construct an AGMF scheme. In order to provide a framework of constructing AGMF, we introduce a new primitive. This primitive is a variant of a key encapsulation mechanism. Firstly, it can be interpreted from the perspective of hash-proof system. And secondly, for some special relations, like the relation of public secret keys, the relation of the encapsulated keys, and the ciphertexts, we require there exist corresponding Sigma protocols. We call this primitive HPS-based CAM supporting Sigma protocols, or HPS CAM Sigma in short. Technically, HPS CAM sigma contains 8 algorithms. Setup outputs a public parameter, and key generation algorithm outputs a pair of public and secret keys. Encapsys algorithm outputs a well-formed ciphertext, and the encapsys star outputs a ciphertext which can be well-formed or ill-formed. And encap key will output an encapsulated key. Decap algorithm will decapsulate a ciphertext to recover its encapsulated key. In addition, check key and check serial algorithm will check whether a key pair or a ciphertext is well-formed, respectively. We also require that there exists sigma protocols for the following relations. The first one, RS, is a relation proving that the keys are valid. And the second one, RCK, is a relation proving that the ciphertext and the key are generated via encapsy and encapk. And the last one, RC star, is a relation proving that the ciphertext is generated by encapsy star. We also require some other properties: universality, unexplainability, indistinguishability, SK second preimage resistance, and smoothness. Please refer to our paper on ePrint for the definitions of these properties and the concrete construction based on DDH. So now, taking HPS CAM sigma as a building block, we can construct AGMF as follows. The setup algorithm is just the setup algorithm of HPS CAM sigma, and the key generation algorithm of judge and users are just the key generation algorithm KG of HPS CAM sigma. To save time, here we only show the algorithm Frank works. Frank will invoke encapsy to generate a ciphertext. Then it calls encapk with the judge's and the receiver's corresponding public keys to generate the corresponding encapsulated keys using the same randomness R. Next, it calls a NISIC to generate the proof, which we will explain in more details later. Finally, the signature includes the NISIC proof pi, the ciphertext, and all the encapsulated keys. The three forge algorithms are modified from the Frank algorithm to guarantee deniability in different compromise scenarios. Here, the ciphertexts are generated by encapsy star, and some encapsulated keys, K, are randomly chosen from the set. Here we provide a high-level description of the relation R for which we can get a NISIC proof. The relation R is built from the three relations of RS, RCK, and RC star from HPS CAM sigma, where RS and RCK are used to guarantee accountability of AGMF, and RC star is for deniability. As we require there are sigma protocols for these subrelations, we can construct a NISIC using the and/or composition techniques and applying the Fate-Shamir transform. For the security of AGMF, we have the following theorem, which bases the security of AGMF on the security of HPS CAM sigma and the security of the Fate-Shamir NISIC proof system. Additionally, we present a lower bound of the signature size in AGMF. Our analysis shows that any AGMF with receiver binding and receiver compromise deniability must have a signature size at least linear in the number n of the members in S. And notably, the signature size of our construction achieves this bound, thus is almost optimal. Here are some references. And that's all of my presentation. If you have any questions, please feel free to contact the authors. Thanks for your listening.
So you're not taking questions? Okay. So let's go. So this closes the session. So now we have a coffee break, and we will continue in half an hour. Thank you.